Hi, welcome back. We are working on finding the continuous time Fourier transform of periodic signals. So I have three examples here, x of t, g of t, y of t, and we're going to start with x of t. So x of t is this periodic square wave, and its pulse width is 2, and its period is 3. So the first thing you need to do is ask yourself, is the signal that I'm looking at periodic? And in this video, that seems obvious because we're only talking about periodic signals. But if you're studying signals and systems on your own, you might, you come up with a signal and you're not sure if it's periodic or not. First question you need to ask yourself, is this periodic? And if the answer is yes, as it is in this case, then the next thing you need to do is find the Fourier series of the signal that you're looking at. So we're going to say that x of t has Fourier series coefficients ak. And we've already found those Fourier series coefficients in a previous video when we looked at the periodic square wave, and we found them to be 2t1 over t when k is equal to 0 and sine of k omega 0 t1 divided by pi k when k is not equal to 0. So T1, if you remember, and I've circled it, T1 is related to the pulse width. In this case, T1 is 1, and T is the period as usual. The period here is 3. And then keep in mind that, as always, the frequency, omega 0, is 2 pi over T, and in our case, that's 2 pi over 3. So what are we dealing with for our specific square wave? Well, 2t1 over t would be 2/3 in our case. Okay, and then the sine of k omega 0 t1, well, omega 0 is 2 pi over 3, and t1 is 1, so we would have sine of k 2 pi over 3 over pi k when k is not equal to 0. Okay, so here are our Fourier series coefficients. Now, in the previous video, we saw that the Fourier transform then is a sum of 2 pi times the Fourier series coefficients times shifted impulses, where omega 0 is 2 pi over 3. Now this is the answer, actually, so this is the Fourier transform. We've completely specified the Fourier series, and we've then said, okay, once you have the Fourier series, here's the Fourier transform. So that's it, except we haven't plotted it yet. So, that might not sit well with you. This looks very complicated. You can impress your friends at parties with this, if that's your thing. But it's not very complicated, and you're going to see that from the plot, actually. So let's plot the omega is equal to 0 impulse. So you see, when we've got an infinite sum, so we're actually going to have an infinite number of impulses, so I can't plot all of them. I'll just plot some of them. But let's plot the k equals 0 term. K equals 0, we have 2/3, so 2/3 times 2 pi is 4 pi over 3, times delta of omega minus 0, k equals 0. So delta of omega minus 0 is an unshifted impulse. So we just have this impulse right here, right here. And it's scaled again by 2 pi times 2/3, 4 pi over 3. There's our impulse. That's one of the impulses, right? Now for the k equals 1 term, we plug in 1 to this guy here. So this would be A1 is equal to sine of 2 pi over 3 over pi. So sine of 2 pi over 3, let's think of the unit circle. That's like this. I think that's the sine of that is root 3 over 2. So I think this is root 3 over 2 pi. And then when we multiply by 2 pi, the 2 pi's go away, and I just have radical 3 times an impulse that is shifted, k equals 1, by 2 pi over 3 to the right. So I'll find 2 pi over 3. Maybe it's here. 2 pi over 3, and remember it's scaled by radical 3. And I can continue on like this. Let's do a couple more. The k equals 2 term, so I plug in 2 to my Fourier series. Sine of 4 pi over 3, sine of 4 pi over 3 divided by pi k, so that's 2 pi. Sine of 4 pi over 3, so that would be over here, so that would be minus root 3 over 2. And then divided by 2, so that would be minus root 3 over 4 pi. And then take that, multiply it by 2 pi, so that gives me minus root 3 over 2. And then times a shifted impulse. K is equal to 2 now, so we have an impulse that's shifted to the right by 4 pi over 3, so that's here. So 4 pi over 3. And we said the amplitude of that thing, or the scaling constant, not the amplitude, the scaling constant is minus root 3 over 2. Okay, and so we can continue on like this. The k equals 3 term, the k equals 4 term, and because we said that this was even, we said that in a previous video, we're going to find that we're going to have exactly the same thing on the left, so at minus 2 pi over 3 and at minus 4 pi over 3. Okay, and those would continue on as well, and what you would see is that this thing follows this sinc function. Here, this is a sinc function in omega, right? And so what we're doing is we're sampling that sinc function. Anyway, that's the Fourier transform. That's x of j omega. And if you take away this red thing that I drew, you see the plot is not very difficult or complicated to understand. So you have to make sense of these mathematical expressions. The impulse is a little bit cumbersome to work with, but really once you start plotting, you see that these things are not too bad to work with. So let's move on. Again, I'm deleting all this stuff, so feel free to pause the video if you need to. Alright, so we're going to go to B now. B is g of t equals sine of 2t. Now, since we used AK in the video already, we're going to use BKs for g of t. But before we do that, actually, again, the first thing you need to ask yourself is this signal periodic? And the sign in continuous time is always periodic. And so the answer is yes. So then you need to find the Fourier series coefficients. So we're looking for the BKs, and we can find the Fourier series coefficients quickly using Euler's formula. We can write g of t as 1 over j2 times e to the j2t minus 1 over j2 e to the minus j2t. And then real quickly we see that this is the first harmonic, right, because omega 0 is equal to 2. And I'm getting the 2 right there. So this is the first harmonic, this is the minus first harmonic, and so we see that B1 is this coefficient 1 over j2, and B minus 1 is this coefficient minus 1 over j2. Okay, so we've got those coefficients, and so now we want the Fourier transform. So g of j omega, so I'm just using capital G here because it's a pair with g of t, but the formula is the same. K goes from minus infinity to infinity of 2 pi times bk, right? I'm using the b's, times delta of k minus and omega minus k omega 0, and omega 0 is 2. So we have that. So this is the answer. We've fully specified the Fourier transform here because we've got the Fourier series coefficients, so those go into the BKs, and then we've expressed the Fourier transform. But that's not good enough. We're going to plot this thing. The question asks us to plot it. So we're going to do so. And this plot is fairly simple as well. even simpler than part A actually. And that's because there are only two non-zero BKs, these two. So even though this is an infinite sum, all of those terms are zero except for these two, the k equals minus one term and the k equals one term. The k equals minus one term, this is, so we'll consider that term first. We have 2 pi times minus 1 over j2, so that's minus pi over j, times a shifted impulse. The impulse has been shifted by omega plus 2, shifted by 2 to the left. 2 to the left. So this would be 2, and this is minus pi over j. Okay, and this is going to be g of j omega. And really, maybe I should be showing the magnitude and the phase, right? The phase of this thing is minus 90 degrees, and the magnitude is pi. But being that it's purely imaginary, I can get away with one plot. Now, the k equals 1 term is the next and last non-zero term. So this is 2 pi times 1 over j2, or pi over j, times delta of omega minus 2. So that's a shifted impulse to the right. So we're going to shift it to the right. And again, this is scaled by pi over j. And put a 2 there. This should be minus 2. And that's the answer. Let's try to understand that real quick, because this is an interesting case, because the sign is so ubiquitous in math and engineering. So let's try to understand this. This says that the sine wave has energy only at two very specific frequencies. So the sine of 2t has energy at omega is equal to 2, unsurprisingly, right? And at omega is equal to minus 2. That's it. There's no energy anywhere else, any frequencies, because this is the sine of 2t. And so it's got equal energy, right? Pi over j minus pi over j, equal energy at those two frequencies. And the two frequencies are, let's see, what is that? So this is 90 degrees, and this is 90 degrees, and this is 90 degrees. So the two frequencies are 180 degrees out of phase with one another. Where I'm getting that is that minus 1 over j has an angle of 90 degrees, and 1 over j has an angle of minus 90 degrees. And so the two are 180 degrees out of phase with one another. All right, so moving on, we're going to go to C. Actually, I'm going to keep B up because C is going to be related to that. So with C, I'm going to call the Fourier series coefficients to be CK, right? Because we haven't used CK yet. We've used A and B. But remember, the first thing I want to ask myself is this signal periodic? Yes. The cosine is always periodic in continuous time. So next, I need to find the Fourier series coefficients, and I can do that quickly with Euler's formula because cosine is related to exponentials in this form, e to the jt times 1/2 plus 1/2 e to the minus j2t, right? And so then I inspect this and I see, well, this is, again, omega 0 is equal to 2, right? Because this is the frequency. And so this is the first harmonic, this is the minus first harmonic. So I see that C1 is that coefficient in front, and C minus 1 is that coefficient in front. And those are the only non-zero coefficients. So then I say y of j omega is equal to the sum from k goes from minus infinity to infinity, 2 pi times ck delta of omega minus 2k. And that's the answer. That's the Fourier transform. I've got the Fourier series coefficients, and then so the CKs are specified, and then this is the form of the answer. And you know, if I wasn't asked to plot, that would be the answer. But I am going to plot, and we're going to see how this plot differs from its cousin there, the sine wave. So let's take the minus 1 term, right? K equals minus 1. This is 2 pi times 1/2, so that's just pi. And then I have a shifted impulse, the k equals minus 1 term, so this is shifted to the left by 2 pi. And this is y of j omega. And then the k equals 1 term, this is 2 pi times 1/2 again, pi. And then I have delta of omega minus 2, so shifted to the right by 2 pi. Right. That's the answer. So let's understand what we have. Again, the cosine has exactly two frequencies. One at, the cosine of 2t has one frequency at 2 and one frequency at minus 2, and it has the same amount of energy at the minus 2 frequency as it does the 2 frequency. Also, those two frequencies are in phase with one another. Their phases are, these are real numbers, so their phases are 0. Their phases are 0, so 0 degrees here, 0 degrees here. That's not what we saw with the sine wave, whose frequencies were 180 degrees out of phase with one another. Further, the sine wave is 90 degrees out of phase with the cosine, because this energy component was 90 degrees, negative 90, and this one is 0, and then this one is 90 degrees, and this one is 0. So the sine is 90 degrees out of phase with the cosine, and the sine has its own frequencies out of phase with one another by 180 degrees, while the cosine has everything nicely in phase with itself.